Our universe is expanding, but we cannot agree on how fast. This is the Hubble tension, a measurement discrepancy that could force us to rewrite the book on modern cosmology. Picture the cosmos as a loaf of raisin bread baking in an oven, each raisin a galaxy drifting apart as the dough expands. If you time how fast a raisin near you moves and compare it to one far across the loaf, you should calculate the same oven temperature, the same expansion history. Yet when our most powerful telescopes perform this cosmic measurement, the nearby and the distant tell conflicting stories. By the end of this journey, you will understand why this single number is causing a crisis in physics, threatening ideas we thought were settled. Could this crack in our model reveal an unknown form of dark energy or a flaw in our most basic assumptions about reality? What do you believe happens when our best maps of the universe no longer match? That single number, the Hubble constant, is more than a measurement. It is the master dial for the entire cosmos. Think of it as the universe's current heartbeat, a rhythm set in motion by the Big Bang itself. Every second, for every 3.26 million light-years of space between two galaxies, the universe adds a little more distance. The Hubble constant tells us exactly how much. If that number is 70 kilometers per second per megaparsec, it means a galaxy 3.26 million light-years away is moving away from us at 70 kilometers every second. A galaxy twice that distance recedes at 140 kilometers per second. This elegant, linear relationship between distance and speed is Hubble's law, the cornerstone of modern cosmology. Getting this number right is everything. It tells us not only how fast the universe is expanding now, but also how to run the cosmic film in reverse. By knowing the current expansion rate, we can calculate backwards to the moment everything began, giving us the universe's age. It calibrates the size of everything we see in the distant cosmos. So when two of the most trusted methods for measuring this fundamental constant start giving stubbornly different answers, it is not a minor calibration error. It is a direct challenge to our story of reality. But how do you actually measure a heartbeat for something as vast as the universe? The first and most direct approach is to build a ladder. Not a physical one, of course, but a cosmic distance ladder, a meticulous chain of measurements that starts right here in our galactic neighborhood and climbs, rung by rung, out into the void. This method is grounded in a simple, powerful idea. If you know how bright something truly is, and you see how dim it looks from here, you can calculate exactly how far away it is. The challenge is finding those reliable cosmic light bulbs, objects with a known, predictable brightness. Astronomers begin with the most basic geometry, using the slight shift in a star's position as Earth orbits the Sun, a technique called parallax, to nail down distances to the closest stars. These become the first solid rung. With that foundation, they look for special stars in nearby galaxies called Cepheid variables. These stars pulse rhythmically, and their pulse rate is directly tied to their true brightness. By studying Cepheids whose distances we already know from that first rung, we learn the precise relationship between their pulse and their power. Now we can find a Cepheid in a more distant galaxy, measure its pulse, know its true brightness, and see how faint it appears. That faintness reveals the galaxy's distance. This is the second crucial rung. Finally, we use those galaxies to find the brightest rung of all, a specific kind of stellar explosion called a Type 1, a supernova. These explosions are so uniform and so incredibly luminous that they can be seen across billions of light years. By observing these supernovae in galaxies whose distances we already know from the Cepheid rung, we can calibrate them as the ultimate standard candles. We then look for the same supernova in galaxies so far away their light has been traveling for most of the universe's history. We see how dim they are, and we know exactly how far that light has traveled. This entire ladder, from local parallax to distant supernova, is a masterpiece of careful, stepwise measurement. It is how we measure the universe's expansion rate in our cosmic present, giving us what is called the local value of the Hubble constant. It is like taking the pulse of the cosmos by checking the nearest galaxies, a snapshot of the universe's recent health. That local measurement, built rung by careful rung, gives us one very precise answer. But there is another way to read the universe's story, one that requires no ladder at all. Instead of looking at nearby galaxies, we can listen to the oldest echo in existence. This is the cosmic microwave background, a faint whisper of radiation that has been traveling for over 13 billion years. It is the cooled and stretched remnant of the universe's first light, released when the hot, dense fog of particles finally cleared and atoms formed. Think of it not as a picture of stars, but as a fossilized imprint of the cosmos itself at the tender age of only 380,000 years. Space probes like the European Space Agency's Planck mission have spent years mapping this afterglow with incredible sensitivity. They did not see a uniform glow, but a tapestry of incredibly subtle variations, tiny patches that were ever so slightly warmer or cooler than the average. These imperfections are not flaws, they are the cosmic seeds. Those slightly denser, warmer spots are the gravitational seeds from which all future structure would grow, the eventual homes of galaxies like our own Milky Way. This map is the ultimate starting condition. Cosmologists take this pristine snapshot of the infant universe and feed it into our most successful model of cosmic evolution, known as lambda cold dark matter. This model is a recipe that includes all the known ingredients of ordinary matter, and dark energy. With the baby picture as the initial condition, we press play. The model simulates billions of years of expansion, gravity pulling matter into structures, and dark energy eventually taking over to accelerate the whole process. It runs the entire cosmic film forward from that ancient moment to our present day. And when it reaches now, it makes a prediction. It tells us what the expansion rate of the universe should be today, given how it began. This is not a measurement of the current pulse, it is a prediction of that pulse based on the universe's first heartbeat. This value, derived from the ancient echo, is the early universe's answer for the Hubble constant. It is a conclusion written in the opening chapter. The two numbers stand in stark opposition. From our local cosmic neighborhood, built on the painstaking ladder of stars and explosions, the universe's expansion rate measures approximately 73 kilometers per second per megaparsec. From the ancient cosmic microwave background, the faded imprint of the infant cosmos, the prediction is significantly slower, closer to 67. On paper, a difference of just 9% might seem trivial, a rounding error in the grand scheme. But in the world of modern cosmology, where measurements are refined to a fraction of a percent, this gap is a yawning chasm. The error bars on these results, the little whiskers that represent uncertainty, do not overlap. They stand apart, clear and defiant. This is not a blur, not a maybe. It is a persistent, statistically significant disagreement that has survived over a decade of increasingly precise observations. This is the Hubble tension in its purest form, a numbers game where the stakes are the very framework we use to understand reality. One number speaks for the universe's recent behavior, the other for its ancient origins, and they refuse to tell the same story. So who is right? Could both be somehow correct, or does this tension reveal a crack in the foundation of everything we think we know? The simplest explanation is often the most appealing. Perhaps we have simply made a mistake. Before we rewrite the laws of physics, we must first check our cosmic math homework with obsessive care. The first and most obvious suspect is the local distance ladder itself. Could a tiny, hidden bias have crept into this chain of measurements? The entire structure relies on perfect calibration. What if our understanding of the Cepheid variable stars, those crucial cosmic metronomes, is slightly off? Interstellar dust is a constant complication, a fine haze that can subtly dim starlight, making a supernova appear farther away than it truly is. Even the instruments on the Hubble Space Telescope, our most trusted eye on the cosmos, have limits to their precision that must be painstakingly modeled and corrected. Teams of astronomers, including Nobel laureate Adam Riess and his colleagues, have dedicated years to this forensic accounting. They have cross-checked every rung, recalibrated instruments, and developed new methods to peer through the dust. The result of this meticulous work is both reassuring and perplexing. While minor refinements have been made, the core discrepancy refuses to vanish. The gap between the local and early universe measurements remains stubborn and statistically solid. This suggests that if an error exists, it is not a simple blunder. It would be a subtle, systemic flaw woven into the very fabric of our measurement techniques, a ghost in the machine that has eluded the world's best detectives. This possibility keeps the search alive, a necessary step before we can confidently declare that the universe itself is hiding a new secret. But if the error is not in our tools, the implications become far more profound. The second potential culprit points not to a mistake in our measurements, but to a gap in our understanding of reality itself. If the local, ladder-based measurement is correct, then the problem may lie in how we interpret the cosmic microwave background and the standard model of cosmology. Our lambda cold dark matter model is a precise recipe, a set of instructions for how the universe evolved. It assumes dark energy is a constant force, dark matter is inert and non-interacting, and that neutrinos have a very specific tiny mass. But what if these are not the final ingredients? What if dark energy was not always the same strength, but instead evolved, growing stronger or weaker over cosmic time? This would dramatically change how the universe expanded from its infancy to the present day. Or perhaps dark matter, which makes up most of the universe's mass, is not completely silent. What if dark matter particles can interact with each other in subtle ways we have not yet detected, changing how structures formed in the early universe? Even a slight adjustment to the mass of neutrinos, the ghostly particles that stream through everything, could shift the model's prediction. Some theorists even propose a brief, early burst of accelerated expansion, a forgotten chapter in the universe's first moments. These are not minor tweaks. They represent new physics, fundamental additions or changes to the rulebook of the cosmos. Any one of these scenarios would alter the path we calculate from that ancient baby picture to our modern universe, potentially bending the predicted expansion rate upward until it finally matches the faster local measurement. This path leads away from calibration errors and into thrilling, uncharted theoretical territory, where the discrepancy is not a problem to solve, but a clue pointing toward a deeper layer of cosmic truth. This brings us to a shadowy figure at the heart of the mystery, dark energy itself. For decades, we have treated this force as a simple, unchanging constant, a steady pressure woven into the fabric of empty space. This was Einstein's cosmological constant, a mathematical placeholder that perfectly fit our observations of an accelerating universe. But the Hubble tension asks a revolutionary question. What if dark energy is not a constant at all? What if it is dynamic, a force that has changed its strength over the vast span of cosmic history? Imagine a universe where dark energy was weak or even dormant in its youth, allowing gravity to build galaxies and clusters without much interference. Then, as the cosmos aged and grew more spacious, this energy awoke and began to grow stronger, pushing galaxies apart with increasing vigor. This scenario would elegantly bridge the gap in our measurements. The early universe, imprinted in the cosmic microwave background, would have formed under the influence of a milder dark energy, leading to the slower expansion rate predicted by our models. But by the modern era, dark energy would have strengthened, accelerating the universe to the faster pace we measure locally. In one move, both measurements could be correct, each capturing a snapshot of a cosmos with a shifting heartbeat. This idea transforms dark energy from a passive background actor into the lead character in an evolving cosmic drama, a concept physicists call quintessence. It challenges a century of assumption and invites us to see the vacuum of space not as empty, but as a dynamic field with its own hidden history. But to truly break this deadlock, we need a referee. We need a third way to measure the universe's expansion, a method that bypasses both the local ladder and the ancient echo entirely. This is where the universe's most violent events become our most precise tools. When two impossibly dense objects like neutron stars or black holes spiral together and collide, they do not just flash with light. They shake the very fabric of space-time, sending out ripples called gravitational waves. These waves are a new kind of cosmic siren, carrying information no beam of light ever could. By analyzing the precise shape of these ripples as they wash over our detectors here on Earth, physicists can reconstruct the event. They can calculate the masses of the colliding objects and, crucially, infer the intrinsic power of the collision itself. Think of it like hearing a bell ring in a fog. From the sound alone, you can tell if it was a tiny handbell or a massive church bell because each has a characteristic ring. A gravitational wave signal works the same way. We know how loud the cosmic bell should ring based on its mass. Then, by measuring how faint or quiet that ringing appears when it reaches us, we can calculate exactly how far away the bell is. This gives us a direct distance measurement, completely independent of stars, supernova, or any rung on the traditional ladder. But we need one more piece. To tie this distance to an expansion rate, we need to know how fast the host galaxy of that collision is moving away from us. That comes from a more familiar tool, light. By finding the galaxy that hosted the merger and measuring the redshift of its starlight, we get its velocity. With both a direct distance from the gravitational waves and a velocity from the light, we have everything we need to calculate a new, independent value for the Hubble constant. This is the promise of observatories like LIGO and Virgo and future space-based missions. They are listening for these cosmic tremors, building a catalogue of events that could settle the debate. Will this third method side with the faster local measurement, or the slower prediction from the early universe? Or, in a twist that would truly upend everything, could it point to a third, completely unexpected answer, revealing that our cosmic map is even stranger than we imagined? At the very heart of this local measurement effort is a team with a singular, almost obsessive focus. The SH0ES Project, which stands for supernova, H0 for the equation of state of dark energy, operates like a cosmic detective agency. Led by Nobel laureate Adam Riess, their mission is to build the most precise cosmic distance ladder ever conceived and to leave no stone unturned in the process. Their strategy is elegantly direct. Instead of constructing a long, winding ladder with many potential weak links, they aim for the shortest possible chain. They use the Hubble Space Telescope to hunt for Cepheid variable stars in galaxies that have, within living astronomical memory, hosted a Type 1, a supernova. This is a brilliant shortcut. By finding both the reliable Cepheid markers and the brilliant supernova standard candle within the same galaxy, they can connect the two directly, bypassing several intermediate and uncertain steps. It is like having a witness who can personally identify both the suspect and the crime scene, creating a far more airtight case. For years, the Hubble Space Telescope has been their primary instrument, its sharp eye peering into these galaxies to pick out the rhythmic pulses of individual Cepheids from the stellar crowds. Yet, even Hubble has its limits. Two persistent ghosts haunted their measurements. The first is interstellar dust, a fine cosmic haze that can dim starlight, tricking astronomers into thinking a star is farther away than it truly is. The second is stellar crowding, where in distant galaxies the light of a Cepheid can blend with the glow of its neighboring stars, making its true brightness difficult to isolate. These were the nagging uncertainties that critics could point to, the potential cracks in an otherwise solid foundation. Then a new eye opened to the universe. The launch of the James Webb Space Telescope provided the SH0ES team with a revolutionary tool. Webb's infrared vision sees right through the dust that obscures Hubble's view. Its incredible resolution can separate individual stars in crowded galactic cores with breathtaking clarity. By training both telescopes on the same targets, the team has performed a cosmic cross-check of unprecedented precision. They are systematically eliminating those last sources of error, confirming the brightness of their Cepheids, and tightening the error bars on their measurement to a razor's edge. The result of this relentless multi-observatory campaign is both a triumph and a deepening mystery. With each new data point, their local measurement of the Hubble constant becomes more precise and more confident. The number holds firm, yet the tension with the prediction from the cosmic microwave background does not ease. If anything, it solidifies. This is the scientific method operating at its most pure and most frustrating. It is a story not of a single eureka, a moment, but of meticulous verification. It is the refusal to ignore inconvenient data, even when that data challenges the most comfortable narratives. The SH0ES team is not trying to prove one side right or wrong. They are simply asking the universe a question with ever greater clarity, and the universe keeps giving the same, stubbornly different answer. While one team sharpens the view of our local cosmos, another has perfected the art of reading the universe's oldest memory. The early universe side of this great debate rests on the shoulders of a single, silent observer, the European Space Agency's Planck satellite. From its vantage point far from Earth between 2009 and 2013, Planck did one thing with unparalleled precision. It stared into the void, collecting the faintest whisper of radiation left over from the Big Bang itself, the cosmic microwave background. This is not a picture of stars or galaxies. It is a thermal imprint, a snapshot of the entire cosmos frozen in time when it was a mere infant, only 380,000 years old. Planck's map is not a smooth, featureless glow. It is a tapestry of exquisite detail, a subtle pattern of warmer and cooler patches across the sky. These tiny fluctuations, mere millionths of a degree in difference, are the cosmic seeds of everything. The slightly denser, warmer spots are the gravitational wells where dark matter and gas began to pool, destined to become the great clusters and superclusters of galaxies we see today. By measuring the precise size and distribution of these spots with extraordinary accuracy, Planck's data allowed cosmologists to deduce the exact recipe of the early universe. They could calculate how much ordinary matter, dark matter, and dark energy were present at that primordial moment, and how fast the universe was expanding back then. This data became the ultimate foundation for our standard model of cosmology, lambda cold dark matter. The model, built on Planck's parameters, is a breathtaking success. It predicts the large-scale structure of the universe, the distribution of galaxies, and the properties of the cosmic web with remarkable fidelity. It explains so much. Yet there is one glaring exception. When this pristine model, born from the infant universe's conditions, is run forward over 13.8 billion years to predict the expansion rate today, it gives a number that stubbornly disagrees with what we measure nearby. This is the profound irony of the Planck legacy. It provided humanity with our most refined and successful cosmic model, a framework that explains nearly everything we see. But in doing so, with its incredible precision, it also exposed the model's most significant potential flaw. Planck's data did not create the Hubble tension. but it crystallized it, turning a curious discrepancy into an undeniable crisis. It stands as a powerful testament to a fundamental truth of science. Sometimes better data does not simply provide better answers. It reveals deeper, more challenging questions, showing us exactly where our understanding of reality might begin to unravel. The cosmic microwave background is not our only window into the universe's infancy. There is another ancient echo, one not written in light, but etched into the very architecture of the cosmos. Billions of years ago, before the first stars flickered on, the universe was a seething ocean of particles and radiation, a thick, hot plasma. In this primordial soup, gravity pulled matter inward, while the intense pressure of radiation pushed it outward. This push and pull created colossal sound waves, ripples that raced through the young cosmos at more than half the speed of light. Then, at the moment of recombination when the cosmic microwave background was released, the music suddenly stopped. The universe became transparent, the pressure dropped, and those sound waves froze in place, their final crests and troughs imprinted as subtle over densities of matter. This is the phenomenon of Baryon acoustic oscillations. Think of it like a stone dropped into a pond, creating ripples that expand outward. If the pond instantly froze solid at a precise moment, you would see those ripples preserved as permanent ridges in the ice. In the cosmos, that frozen ripple is a specific, measurable distance, a standard ruler etched into the sky. That ruler is about 500 million light-years long. Today, when we map the universe on its largest scales, we do not see a random sprinkling of galaxies. We see a subtle, statistical preference for galaxies to be separated by this specific scale, the fossilized imprint of those ancient sound waves. It is a ghostly pattern, a whisper from the first 400,000 years, telling us the exact dimensions of the infant universe. By conducting enormous surveys of millions of galaxies, projects like the Sloan Digital Sky Survey and the Dark Energy Spectroscopic Instrument, or DAISY, can measure this standard ruler with incredible precision. They look across vast cosmic distances, see how this ruler appears to our eyes, and from that perspective, they can calculate how much the universe has stretched since those sound waves were frozen. This provides a direct, powerful measurement of the expansion history, a check on the story told by the cosmic microwave background. The results from these Baryon acoustic oscillation surveys are telling, and for the standard model, they are reassuring. They consistently point toward the same, slower expansion rate predicted by the Planck satellite's map of the early universe. It is a powerful, independent confirmation that our reading of the cosmos's first chapter is fundamentally sound. Yet, the plot refuses to simplify. When scientists combine these early universe Baryon acoustic oscillation measurements with certain types of local data, like the brightness of distant supernova, new and subtler wrinkles appear. The numbers do not align perfectly. It is as if the universe is offering two different, yet corroborating early universe testimonies that agree with each other. But when we try to stitch them seamlessly to the modern era, the thread still pulls taut. This does not resolve the Hubble tension, it deepens it. It suggests the mystery may not be a single error in one measurement, but a more complex disconnect woven through the entire cosmic timeline. Each new, precise tool we invent does not bring a clearer answer, but instead reveals a richer, more intricate puzzle, inviting us to look even deeper. This chronological conundrum strikes at the very timeline of existence. The Hubble constant holds a simple, yet profound, mathematical relationship with the age of the cosmos. A faster expansion rate today means the universe reached its current size more quickly, pointing to a younger age. A slower rate suggests a more leisurely, older universe. The numbers tell two very different stories. The faster local measurement implies a cosmos only about 12.5 billion years old. The slower, early universe prediction from the cosmic microwave background gives us the familiar figure of 13.8 billion years. That gap of over 1 billion years is not a minor rounding error. It represents a vast, silent epoch, a stretch of time longer than the entire history of life on our own planet. This is far more than an academic disagreement about dates. It forces us to confront a fundamental question about cosmic history. When did the lights first turn on? Our current models, built on the older age, describe a patient, gradual awakening. After the Big Bang, the universe cooled into darkness for hundreds of millions of years, a period cosmologists call the Dark Ages. Slowly, gravity pulled the faintest wisps of gas together until the first stars ignited, their fierce ultraviolet radiation burning away the fog of primordial hydrogen in an era known as reionization. Eventually, these stars gathered into the first small, fragile galaxies. This entire sequence fits comfortably within a 13.8 billion-year timeline. But if the universe is actually 12.5 billion years old, that timeline collapses. Over 1 billion years of development time simply vanishes. Astrophysicists would then face an extraordinary challenge. They would need to explain how the first stars, galaxies, and gigantic black holes managed to form and mature at breakneck speed. It would be like watching a child grow from infancy to adulthood in half the expected time, forcing us to reconsider every stage of their development. This faster timeline could demand drastic revisions to our understanding of the cosmic dawn. Perhaps dark matter, the invisible scaffolding of the universe, played a more active role in clustering matter together sooner than we thought. Maybe the first stars were unimaginably massive and short-lived, seeding the cosmos with heavy elements at a ferocious pace. The age discrepancy is not just about a number. It is about the entire narrative of how a hot, featureless beginning transformed into the rich, structured universe we see outside our window tonight. One of the most compelling theoretical paths out of this deadlock introduces a ghost into the machine of the early universe. Cosmologists call it early dark energy. This is not the dark energy we know today, the constant force accelerating our modern cosmos. Instead, it is a hypothetical, short-lived phenomenon, a phantom that flickered into existence for a mere cosmic instant during the universe's first few 100,000 years. Picture the infant cosmos not as a steadily inflating balloon, but as one that received a sudden, sharp puff of air right before it froze into the snapshot we see in the cosmic microwave background. This brief, extra burst of expansion would have left a distinct fingerprint. It would have subtly changed the size of the universe's most important measuring stick, the sound horizon from those primordial Baryon acoustic oscillations. That frozen ripple, that standard ruler, would be a bit smaller. Now think about the cosmic microwave background map. We measure the angular size of those hot and cold spots on the sky with incredible precision. If the actual physical ruler that created them was smaller than our standard models assume, then to make those spots appear the same size to us today, the universe must have expanded more overall in the time since. The mathematics is elegant and direct. A smaller early ruler forces a faster modern expansion rate to make the geometry work. In one move, early dark energy could reconcile the two conflicting numbers. The cosmic microwave background prediction would shift upward, finally meeting the local measurement from supernova and Cepheid stars without breaking anything else in our model. It is a clever patch, a theoretical adjustment that saves our core understanding of cosmology by adding a new, transient chapter to its first page. Yet for all its elegance, early dark energy remains a phantom, a mathematical possibility without direct observational proof. Its existence is inferred solely from the tension it seeks to resolve. This is the creative, often frustrating, work of theoretical cosmology. When the data presents a stubborn conflict, scientists do not just discard their life's work. They stress-test it, probing for weak spots and imagining what forgotten ingredients could have been present at the dawn of time. Early dark energy is one such ingredient, a testament to the ingenuity required when the universe itself seems to contradict its own story. Into this high-stakes observational standoff now steps a new witness with unparalleled sight. The James Webb Space Telescope is not merely another instrument, it is a revolutionary leap in our ability to see the cosmos. Its position far from Earth, coupled with its massive gold-coated mirror and suite of infrared instruments, gives it a superpower. It sees through the cosmic dust that has long clouded our view, and it resolves individual stars in galaxies millions of light-years away with breathtaking sharpness. For the teams painstakingly building the cosmic distance ladder, Webb is the ultimate forensic tool. It is being trained directly on those critical Cepheid variable stars in galaxies that have hosted supernovae. Before Webb, measuring a Cepheid's brightness in a distant, dusty galaxy was an exercise in estimation and correction. Astronomers had to model the dimming effects of dust, introducing a layer of uncertainty. Now, Webb's infrared eyes cut through that haze, seeing the star's true glow. It can also separate the light of a single Cepheid from the crowded stellar neighborhood around it, eliminating another major source of error. This allows for a direct, clean measurement, a recalibration of the ladder's most important rungs from the ground up. The early data is already flowing in, and it is performing exactly as hoped, providing crystal-clear readings that confirm the existing measurements with even tighter margins of error. This is where the plot twists. If Webb's pristine data simply reinforces the faster local expansion rate, it does not bring us closer to a resolution. Instead, it deepens the mystery by systematically eliminating the last plausible observational errors. The dust, the crowding, the calibration quirks. It makes the case for a systematic mistake far less tenable. It strengthens the local measurement to such a degree that ignoring it becomes scientifically untenable. The telescope's incredible power, therefore, pushes us toward a more thrilling, yet more daunting conclusion. It makes the argument for new physics not just plausible, but increasingly urgent. Webb stands at this observational crossroads, a silent judge collecting evidence. With every confirmed Cepheid, every clarified supernova, it is not answering the central question, but refining the question itself. It is forcing the universe to state its case with perfect clarity, setting the stage for a moment of truth where the only remaining explanation may be that our cosmic model is missing a fundamental piece. The data is clear, but its meaning is a question that reaches far beyond our telescopes. This is not merely a puzzle about numbers. The Hubble tension forces us to confront a deeper, more philosophical uncertainty about the nature of our knowledge itself. For a generation, the lambda cold dark matter model has stood as the definitive story of the cosmos. It has predicted the large-scale structure of the universe, explained the abundance of light elements, and accounted for the cosmic microwave background with stunning accuracy. It has been our most successful map of reality, passing every major observational test for decades. Now, a single, persistent discrepancy threatens to reveal a crack in its very foundation. This presents a profound choice for the future of cosmology. Is our magnificent model simply incomplete, missing one final ingredient like a transient burst of early dark energy? Or are we standing at the precipice of something far more revolutionary, where the model itself is fundamentally flawed, requiring a new framework entirely? History offers a sobering parallel. For centuries, Newton's laws of motion and gravity described the heavens with perfect precision. They predicted the orbits of planets and the pull of the tides. Yet tiny anomalies in Mercury's orbit persisted, a whisper that something was amiss. Scientists searched for a hidden planet, for minor tweaks to the equations. The answer, when it came from Einstein, was not an adjustment. It was a complete reimagining of gravity, space, and time itself. General relativity did not just fix Mercury's orbit. It rewrote our understanding of the universe on its most basic level. The Hubble tension today carries that same electric potential. It humbles us, serving as a powerful reminder that our maps of reality are always provisional. They are the best stories we can tell with the evidence we have, but they are not the final word. This tension, this stubborn disagreement between our best measurements, is not a failure of science. It is the essence of science. It is the process laid bare, a living demonstration that our understanding grows not by clinging to comfortable facts, but through the relentless, often uncomfortable, pursuit of questions that challenge everything we think we know. This persistent clash of numbers has sparked a quiet revolution in how cosmologists talk to one another. A community accustomed to consensus now finds itself in a state of healthy, productive division. On one side, a growing number of theorists see the Hubble tension as an undeniable beacon, a signal flashing from the darkness that our map of reality is incomplete. They are actively building new models that stretch beyond the comfortable confines of lambda cold dark matter, proposing exotic additions like that fleeting early dark energy, or forms of dark matter that interact, or even subtle changes to the fundamental nature of gravity itself. For them, the discrepancy is too large, too persistent, and too reinforced by independent methods to be anything but a clue. It is an invitation to explore. On the other side stand the meticulous skeptics, the guardians of rigor. They argue that extraordinary claims require extraordinary evidence, and that before we rewrite the textbooks, we must exhaust every possibility of a more mundane explanation. They dive deep into the error budgets of the supernova measurements, questioning the subtle assumptions about dust in distant galaxies. They re-examine the cosmic microwave background data, probing for any subtle bias in how we separate its signal from the foreground glow of our own Milky Way. Their work is not born of stubbornness but of profound respect for the scientific process. This divide is not a sign of a field in crisis. It is the sound of a field doing its job correctly. Walk into a cosmology conference today, and you will feel the vibrant energy of this debate. Presentations are followed by intense, respectful discussions over coffee. Whiteboards fill with equations as researchers from both camps test each other's ideas. They argue over statistical priors and the interpretation of error bars, not out of conflict, but from a shared desire to get it right. This dynamic, sometimes contentious environment is the engine of discovery. It ensures that every potential systematic error is hunted down with relentless precision, and every wild new theory is subjected to the coldest, hardest scrutiny. The result is that any eventual resolution to the Hubble tension, whether it points to a hidden error or a new law of physics, will have been vetted from every conceivable angle. This rigorous collective interrogation does not weaken our final understanding. It forges it, making the conclusion we eventually reach far stronger and more trustworthy than any single team or telescope could provide alone. Yet another number refuses to cooperate. Alongside the battle over expansion, a second, quieter disagreement simmers in the background of cosmology. This is the S8 tension, and it asks a different but equally fundamental question about our universe. How clumpy is it? When we look at the grand tapestry of the cosmos, matter is not spread out evenly like butter on toast. It is gathered into a vast cosmic web, with dense clusters of galaxies connected by filaments and separated by enormous, empty voids. The S8 parameter is a single value that tries to capture this overall level of lumpiness, quantifying how much matter has gathered into structures over time. To measure it, scientists again turn to their two most powerful tools. The cosmic microwave background provides a pristine starting point. The subtle patterns in that ancient light tell us exactly how much potential for clumpiness was baked into the infant universe, the seeds from which everything grew. Running our standard model forward from those seeds predicts how clumpy the universe should be today. Separately, astronomers use a clever technique called weak gravitational lensing to measure the actual clumpiness we see now. This involves observing how the gravity of all the invisible dark matter and visible matter in the cosmos distorts, or lenses, the light from billions of background galaxies. It is like looking at a city's skyline through a giant, warped pane of glass, the distortions revealing the mass of everything in between. These two methods should agree, but they do not quite. The cosmic microwave background suggests the universe today should be slightly more clustered, a bit lumpier than what the weak lensing surveys actually measure. The gap is small, but it is persistent. This is not about how fast the universe expands, but about how its contents are arranged. While distinct from the Hubble tension, a fascinating possibility begins to emerge. Could these two independent discrepancies be connected? Some theorists suspect they might be two different symptoms of the same underlying illness in our cosmic model. Perhaps dark matter is not completely cold and inert. If dark matter particles had a tiny amount of intrinsic motion or could interact with each other, it could subtly change how structures form. This could reduce the clumpiness we see today, easing the S8 tension, while also altering the expansion history in a way that affects the Hubble constant. Alternatively, what if gravity itself behaves differently on the vast scales of the cosmic web than our equations predict? A modification to the laws of gravity could simultaneously shift how fast the universe expands and how matter gathers within it. The idea is compelling. One unexplained anomaly might be a curiosity, but two stubborn, independent discrepancies begin to look like a pattern. They hint that the flaw is not in our observations, but in the foundational recipe we use to interpret them. Solving the mystery of the universe's expansion rate might, in a single stroke, also explain why its structure appears just a little smoother than our best models expect. This transforms the challenge from fixing two separate bugs to searching for one elegant correction, a single missing piece of physics that could make the entire cosmic picture snap into focus. The resolution to this cosmic standoff may ultimately come not from a single telescope, but from a flood of data so vast it redefines our vision of the sky. On a remote mountaintop in Chile, a new eye on the universe is being prepared, one with the power to watch the entire cosmos in motion. The Vera Rubin Observatory, with its enormous mirror and 3.2 gigapixel camera, is not designed to stare at one galaxy for weeks. Its purpose is to capture the whole accessible sky over and over again for an entire decade. This monumental project, called the Legacy Survey of Space and Time, will begin its work in the middle of this decade, and it promises to transform cosmology from a field of careful, targeted studies into a science of sheer statistical abundance. Night after night, its automated gaze will record the positions, movements, and brightness of billions upon billions of galaxies, stars, and transient events. It will discover millions of supernovae, not just the rare, perfectly placed ones we study today, but a whole population in every corner of the sky. This changes the game entirely. With such an enormous sample size, astronomers can build a new, independent cosmic distance ladder from the ground up, using statistical methods that are immune to the quirks of any single galaxy or dusty patch of space. They will measure the local expansion rate by watching how entire populations of supernovae dim with distance, a measurement so robust it could settle the local side of the debate through sheer weight of numbers. But the observatory's power goes far beyond just measuring expansion. By tracking the subtle distortions in the shapes of billions of galaxies caused by weak gravitational lensing, it will create the most precise map ever made of the universe's dark matter skeleton and its clumpiness. This will deliver an exquisitely detailed measurement of the S8 parameter, that other lingering tension about cosmic structure. For the first time, we will have a single, unified dataset capable of measuring both how fast the universe is expanding and how its matter is arranged, two fundamental probes that currently tell conflicting stories. The true breakthrough may lie not in a single headline-grabbing number, but in the patterns hidden within this ocean of data. The Hubble tension might be resolved by discovering a subtle, previously invisible correlation, a systematic effect that only reveals itself when you have millions of examples to compare. Or the data may show with undeniable clarity that the discrepancy is real, pushing us irrevocably toward new physics. The Vera Rubin Observatory offers a fresh, unbiased perspective, a chance to listen to the universe's story told not through a few carefully chosen sentences, but through the entire book. It is our best hope for breaking the logjam, for providing the clear, statistical verdict that will guide cosmology into its next great chapter. There is another, more philosophical layer to this entire puzzle. We are not just observers of this cosmic drama, we are participants living within it, at a very specific moment in the universe's long story. This leads to a profound, almost unsettling question. Is it merely a coincidence that we exist in the precise era when these two powerful methods for measuring the cosmos diverge? The cosmic microwave background gives us a pristine view of the ancient universe, a baby picture from over 13 billion years ago. Our local measurements using stars and supernovae capture the universe's recent behavior, its current heartbeat. We happen to live in the narrow slice of cosmic time where both of these windows are open to us, where we have the technology to peer through each one with incredible precision. And in this unique era, they tell us conflicting stories. This is the Anthropic Perspective. It suggests that our viewpoint is not neutral or privileged. The very fact that we are here to take these measurements might be influencing the story they tell. Perhaps we exist in a special transitional period, a cosmic moment when the expansion rate is shifting in a way that makes the past and present appear mismatched. This idea does not offer a scientific solution, but it serves as a crucial reminder of a principle that dates back to Copernicus. We do not occupy a central or special place in the universe. Our observations are always filtered through the lens of our specific time and location in cosmic history. Any complete theory of the cosmos must ultimately account for the observer, for the fact that the universe we measure is the one that allowed creatures like us to exist within it and ask these very questions. It humbles the search, framing the Hubble tension not just as a problem in our equations, but as a potential clue about our own place in the unfolding narrative of everything. The search for answers has now moved into the realm of pure possibility, inside the most powerful supercomputers on Earth. When direct observation presents a paradox, scientists turn to simulation, building entire digital universes from scratch to see which rules could make our reality possible. These are not video games, but meticulous mathematical laboratories where the laws of physics themselves become variables. Cosmologists start with the basic recipe of the standard model, then introduce a single speculative change. What if dark energy was not constant but evolved like a field slowly gaining strength? They adjust the equation and let the simulation run. What if neutrinos, those ghostly particles, have a slightly different mass than we assume? They tweak the parameter and press start. They even dare to modify the law of gravity itself on cosmic scales, testing frameworks that go beyond Einstein's relativity. Each simulation then unfolds over billions of virtual years. Gravity pulls digital dark matter into a cosmic web. Virtual galaxies form and cluster. The entire history of a universe, from a hot, dense state to a vast, expanding cosmos, plays out in a matter of weeks on a bank of processors. The crucial moment comes at the end. The scientists inside the simulation become the observers. They generate a virtual cosmic microwave background from their digital infant universe and analyze its patterns. Do they match the exquisite details from the Planck satellite? If not, that version of physics is discarded. But if the simulated CMB is a perfect match, they proceed to the next test. They then place a virtual astronomer inside that digital cosmos, at a point in time analogous to our present day. That astronomer builds a virtual distance ladder, measuring the expansion rate using simulated Cepheid stars and supernovae. This is the ultimate check. Does this simulated universe, which perfectly replicates our ancient past, also produce a faster modern expansion rate, finally bridging the gap? When a simulation passes both of these monumental tests, it ceases to be a mere experiment. It becomes a serious candidate for reality, a blueprint for a cosmos that looks exactly like ours in every way we have measured, yet operates by a subtly different set of rules. These digital laboratories allow us to perform the ultimate thought experiment, to run a billion-year cosmic experiment overnight, offering a glimpse into worlds governed by physics we have only just begun to imagine. The true power of this cosmic mystery lies not just in the numbers, but in the questions it forces all of us to ask. How old is everything around us? What unseen ingredients make up the fabric of reality? Where is this grand expansion ultimately leading? These are not puzzles for scientists alone. They are the very same wonders that have captivated humanity since we first looked up at a star-filled sky. The Hubble tension transforms those ancient wonders into a living, breathing detective story unfolding in real time. We get to watch as brilliant minds confront contradictory evidence, as engineers build ever better telescopes to chase down clues, and as theorists dare to imagine wild new possibilities. This process reveals a beautiful truth about science itself. It shows us that even our most successful and celebrated theories are not sacred, unchanging doctrines. They are the best maps we have, always subject to revision when the terrain itself presents a new, unexpected feature. The universe, it seems, is still capable of profound surprise. This engagement turns abstract cosmology into something deeply human, a shared adventure in understanding. It invites everyone to follow along, to feel the thrill of not knowing, and to appreciate the collective effort to find out. For a student gazing at a textbook, or for anyone who has ever felt a sense of awe on a clear night, this ongoing saga is a powerful reminder. The greatest story, the story of everything, is still being written, and we all have a front row seat to the chapter where the plot took a fascinating, mysterious turn. While we gaze upward seeking answers about the cosmos, the search itself is quietly transforming our world here on Earth. The Hubble tension is more than a theoretical puzzle. It is a powerful engine for innovation. To measure the faintest whispers from the edge of time, we must build machines of breathtaking sensitivity and develop new ways to think about information. This relentless push for precision creates technological ripples that spread far beyond astronomy. Consider the detectors at the heart of telescopes like the James Webb Space Telescope or the Planck satellite. They must register individual photons of infrared light or subtle variations in temperature 1,000,000 times fainter than anything our eyes can see. The struggle to build such exquisite sensors directly advances the field of photonics, leading to more sensitive medical imaging devices that can detect illnesses earlier and with less intrusion. The same algorithms developed to clean cosmic microwave background data from the glow of our own galaxy are now used to sharpen medical scans, separating a tumor's signal from the noise of healthy tissue. Even the software that models the expansion of the universe relies on cutting-edge computational techniques that eventually filter into weather prediction, financial modeling, and artificial intelligence. The quest to map the cosmic web demands we process petabytes of data, pushing the boundaries of computing and data transmission, which in turn strengthens the global digital infrastructure we all rely on every day. This is the hidden economy of curiosity, where investing in a fundamental question about the universe pays dividends in technologies that improve and save lives. Beyond the hardware and software, these monumental projects are human endeavors, international collaborations involving thousands of scientists, engineers, and technicians from dozens of countries are the norm in modern cosmology. Teams working on the Vera Rubin Observatory, the Planck mission, or the gravitational-wave detectors must learn to communicate across languages and cultures, solving not only cosmic mysteries but also the intricate challenges of global cooperation. These projects become incubators for the next generation of problem solvers, students and early career researchers trained in these high-stakes, collaborative environments learn a unique blend of technical rigor and creative systems thinking. They graduate not just as astronomers, but as experts in data science, optical engineering, and complex project management, skills they carry into industries that drive our technological future. The value of understanding a single number like the Hubble constant, therefore, cannot be measured in light years alone. It is also measured in the new medical devices on hospital shelves, the robustness of our global communications networks, and the brilliant minds equipped to tackle the great challenges of our time. The drive to comprehend the cosmos, it turns out, helps us build a better world right here at home. For any teacher looking to bring science to life, the Hubble tension is a gift. It is not a dusty fact from a textbook, but a live, unfolding case study happening right now. It perfectly demonstrates the scientific method not as a neat, linear checklist, but as the messy, thrilling, and collaborative process it truly is. Students can trace the entire cycle. They start with the observations, the meticulous data from telescopes like Hubble, Webb, and Planck. They see the models built from that data, the elegant lambda cold dark matter framework that explains so much. Then comes the crucial moment of discrepancy, the stubborn numbers that refuse to agree. This is where real science begins, not ends. Instead of ignoring the conflict, the global community of cosmologists leans into it, generating a spectrum of new hypotheses, from hidden measurement errors to revolutionary ideas like early dark energy. Students can watch this debate play out in near real time by following scientific press releases, reading simplified summaries of new papers, or even accessing the actual data from public archives. This connects abstract concepts from physics, advanced mathematics, and statistical analysis to a tangible, high-stakes mystery. It shows that science is not a collection of settled answers, but a dynamic conversation with the universe. Textbooks become not final authorities, but progress reports from the frontier, always one discovery away from an exciting revision. This ongoing saga makes cosmology feel immediate and relevant. It teaches a powerful lesson about intellectual humility and courage. It shows that uncertainty is not a sign of failure, but an invitation to explore more deeply, proving that the greatest stories are those where we have not yet reached the final page. This rigorous process of verification is not confined to a single laboratory or team. In a debate of this magnitude, where the very foundations of cosmology are being tested, independent analysis becomes the ultimate safeguard. Think of it as a global peer review, conducted not just on the final conclusions, but on the raw data itself. Different research groups around the world take the same treasure trove of numbers from telescopes like Hubble, Planck, or the James Webb Space Telescope, and they feed them into their own independent computational pipelines. Each team makes its own educated choices about how to filter out background noise, how to model the subtle effects of interstellar dust, and which statistical priors to apply when interpreting the faint signals. They are essentially asking the same question of the universe, but using slightly different dialects of mathematics. This independent crowdsourcing of analysis serves a vital purpose. It helps to identify hidden biases or subtle computational errors that might inadvertently creep into any single group's work. If one team's unique method produced a wildly different result, it would point to a flaw in their specific approach. But the reality is far more compelling. Multiple independent teams, starting from different philosophical and technical starting points, are converging on the same stubbornly conflicting answers. The local universe measurements consistently point to a faster expansion, while the early universe data just as consistently predicts a slower one. This independent convergence is what transforms a curious discrepancy into a credible crisis. It tells us the tension is not an artifact, not a ghost in one particular machine. It is a signal that persists no matter who is listening or how they tune their instruments. This collective, often contentious scrutiny is not a sign of a broken system. It is the bedrock of reliable scientific progress, a slow and careful distillation of truth from a universe that rarely makes things easy. These moments of profound uncertainty are not new to the story of astronomy. In fact, they are its very heartbeat. Throughout history, the cosmos has presented us with tiny, nagging inconsistencies that refuse to fit our beautiful models, and each time, those cracks became the doorways to a deeper reality. Consider the orbit of Mercury. For centuries, Isaac Newton's laws of gravity described the clockwork motion of the planets with stunning accuracy. Yet Mercury, the innermost planet, exhibited a faint wobble in its path, a slow rotation of its elliptical orbit that Newton's equations could not fully explain. The discrepancy was minuscule, just 43 arcseconds per century, a shift so small it could be covered by the width of a human hair held at arm's length. Many tried to explain it away, proposing an unseen planet, dubbed Vulcan, orbiting near the Sun, or suggesting slight adjustments to the math. But the anomaly persisted, a quiet but persistent whisper that something in our understanding of gravity was incomplete. That whisper was only answered when Albert Einstein introduced his theory of general relativity, which reimagined gravity not as a force, but as the curvature of spacetime itself. When Einstein applied his new equations to Mercury's orbit, the anomalous precession emerged perfectly, without any need for invented planets or fudged numbers. A tiny flaw had revealed a fundamental truth. A similar story unfolded much more recently beneath the very surface of our Sun. For decades, physicists detected fewer neutrinos, those ghostly subatomic particles, streaming from the Sun's core than their models predicted. This was the famous solar neutrino problem. The math of nuclear fusion was clear, the detectors were precise, yet the numbers stubbornly refused to match. Was our understanding of the Sun's powerhouse wrong? The answer, once again, pointed not to an error in our stellar models, but to a gap in our knowledge of physics itself. We discovered that neutrinos are not static. They oscillate, changing their identity between three different types as they travel. The detectors on Earth were only catching one kind, missing the others that had transformed along the journey. This discrepancy did not break our model of the Sun. It completed our model of the universe, revealing a fundamental, dynamic property of one of its most elusive particles. The Hubble tension stands firmly in this noble lineage of great anomalies. It is not an embarrassment for cosmology, but its current frontier. Like Mercury's wobble or the missing neutrinos, this persistent gap between measurement and prediction is a signpost. It is the universe's way of telling us that our map, however detailed and successful, is still missing a crucial feature. History teaches us that the most productive response to such a signpost is not to dismiss it or explain it away with increasingly complex patches, but to have the courage to follow where it points. It invites a thrilling humility, reminding us that our greatest theories are not in points, but waypoints in an endless journey of discovery. The resolution to this tension, whether it reveals a new property of dark energy, a subtle interaction of dark matter, or something entirely unforeseen, will not shatter our understanding. It will expand it, weaving a new thread into the grand tapestry of cosmic law and gifting our generation a deeper story of everything. The search for this missing piece is now drawing ideas from the very edges of physics. To mend a crack in our cosmic model, cosmologists are looking beyond their own telescopes, borrowing tools and concepts from fields that study reality at its most fundamental. They are turning to the world of particle physics, where scientists model the behavior of matter and energy at scales smaller than an atom. Could the early universe have been home to a fleet of exotic, short-lived particles we have not yet detected? Particles with strange properties that briefly influenced the rate of expansion before vanishing without a trace. These hypothetical entities with names like sterile neutrinos or action-like particles are not invented to solve this one problem. They emerge naturally from theories trying to unify the fundamental forces. If they existed, even for a fleeting moment after the Big Bang, their unique energy could have given the cosmos that extra, early push, subtly changing the sound horizon and neatly explaining the faster expansion we see today. This is not just borrowing a tool, it is connecting two great stories: the story of the universe's birth and the story of what the universe is made of. The conversation grows even more speculative and more fascinating when we invite string theory to the table. This ambitious framework suggests that the fundamental particles we see are not points, but tiny, vibrating strings. To make the mathematics work, these strings must vibrate in a universe with more than the three spatial dimensions we experience. While still theoretical, this idea offers a breathtaking possibility for cosmology. What if the dark energy accelerating our universe is not a new, separate substance, but a consequence of these extra dimensions slowly evolving over cosmic time? Or what if it is the manifestation of a fundamental scalar field, a kind of cosmic weather that permeates all of reality, whose pressure has been changing since the dawn of time? String theory provides a rich landscape of mathematical possibilities for such fields, offering cosmologists a new vocabulary of potential solutions to the Hubble tension. This cross-pollination of ideas is transforming the quest. Cosmology is no longer an isolated science of distant galaxies. It is becoming the ultimate testing ground for theories of everything. A single, precise measurement of the universe's expansion rate could, in principle, validate or rule out versions of these highly abstract theories. It creates a powerful feedback loop. The largest questions about the cosmos now guide the search in the smallest realms of particle accelerators, and potential discoveries in subterranean detectors could rewrite the first chapter of our cosmic history. This unity reveals a profound truth about our pursuit of knowledge. The universe does not respect the artificial boundaries we draw between scientific disciplines. The behavior of the entire cosmos is inseparably linked to the nature of its most basic building blocks. A revolution in our understanding of dark energy or the early universe would not just be a victory for astronomy. It would be a seismic event for all of physics, echoing from the vast expanse of intergalactic space down to the quantum foam of spacetime itself. Behind every measurement of the distant cosmos lies a profound choice made right here on Earth. The pursuit of this single number, the Hubble constant, is not a cheap endeavor. It demands the collective work of generations, the focused labor of thousands of brilliant minds, and instruments of almost unimaginable cost. The James Webb Space Telescope represents an investment of $10 billion. The upcoming Vera Rubin Observatory will cost well over $500 million. Supercomputers hum for months, consuming vast energy to simulate universes that do not exist. In a world confronting immediate and urgent challenges, from environmental shifts to global health and inequality, it is natural and necessary to ask a difficult question. Is this worth it? When we fund a telescope that looks backward in time, what are we choosing not to fund down here on the ground? This is the ethical dimension of big science, a quiet conversation happening not in observatories, but in the halls of governments and in the minds of a thoughtful public. It forces a civilization to define its own ambition. Proponents of fundamental research offer a compelling counterpoint. They argue that you cannot put a price on wonder or on the expansion of human knowledge for its own sake. The drive to understand our place in the cosmos is a fundamental part of what makes us human. It is the same urge that propelled explorers across oceans and pioneers into space. This pursuit, they say, is not a diversion from our problems, but a vital source of the tools and the spirit we need to solve them. The technological fallout from building a Webb or a Hubble is immense. The exquisite infrared sensors developed to see the first galaxies are now refining cancer detection, the algorithms that clean cosmic data to sharpen medical scans. The global collaborations forge new methods of international cooperation and train generations of problem solvers whose skills ripple through every sector of our economy. This is the hidden yield of curiosity-driven science. It builds a more capable, interconnected, and innovative society, often in ways that are impossible to predict at the outset. Yet the argument for balance remains powerful and essential. It is not a call to stop looking up, but a plea to ensure we are also looking around and looking after one another. The most ethical path forward is not an either-or proposition, but a both-and commitment. It requires transparent dialogue about the tangible benefits of fundamental research, a steadfast dedication to ensuring those benefits are shared broadly, and a funding ecosystem that can support both the urgent needs of the present and the profound questions of eternity. This debate at its heart is about more than budgets. It is a reflection of what we value. Do we see ourselves merely as inhabitants of a planet managing its crises? Or do we see ourselves as citizens of a universe with a destiny that includes understanding it? Investing in cosmic mysteries is a statement of faith in the human mind and in the future. It says we believe there will be a tomorrow worth preparing brilliant minds for, and that part of that preparation is continuing the oldest story we have, the story of trying to read the stars. The resolution to the Hubble tension may come from a brilliant insight or a new machine, but the permission to seek that resolution comes from a societal choice, a collective decision about the kind of legacy we wish to build. The most precise measurements in history are not produced by machines alone, but by the people who live with the data. For every point on a light curve, every subtle temperature fluctuation in the cosmic microwave background map, there is a story of human dedication. Picture a graduate student in a quiet office long after midnight, their eyes tracing the rhythmic pulse of a Cepheid variable star on a screen. This is not a glamorous moment. It is the painstaking work of measuring brightness, accounting for dust, and checking for errors over and over across hundreds of stars. One misstep in this foundational analysis could ripple up the entire cosmic distance ladder, yet this individual's quiet perseverance builds the very rungs we stand on. Their story is one of meticulous care, a testament to the fact that our grandest cosmic maps begin with someone choosing to look with unwavering patience at a single point of light. Then there is the theorist, perhaps once considered a bit of an outsider, who scribbled equations for a wild idea on a whiteboard a decade ago. Their concept of a fleeting burst of early dark energy was initially met with polite skepticism. Yet as the Hubble tension refused to fade, that speculative notion transitioned from the fringe to a leading hypothesis discussed in major conferences. Their journey embodies the creative courage science requires, the willingness to propose something strange because the data itself is strange. It is a story of intellectual resilience, where a personal hunch evolves through rigorous peer critique into a potential key for unlocking a universal mystery. We must also remember the engineers whose names rarely appear in headline scientific papers. One individual might have spent years perfecting a single, hypersensitive filter for the Planck satellite, a component critical for isolating the primordial whisper of the cosmic microwave background from the overwhelming glare of our own galaxy. Their triumph was not a discovery, but a silent victory of purity and precision, enabling the entire field to see the infant universe with unprecedented clarity. Their contribution is a profound reminder that every great leap in understanding is built upon 1,000 small, perfect solutions. These personal narratives weave together into the larger fabric of the endeavor. Science, at its heart, is this collective human project. It thrives on late-night conversations over coffee, on the frustration of a failed observation that leads to a better method, and on the shared exhilaration when independent teams confirm a difficult result. The Hubble tension is not just a conflict between numbers, it is a conversation among thousands of curious minds across the globe, each bringing their unique skill and perspective to a common table. This human dimension transforms the abstract into the intimate. It reminds us that the drive to comprehend our place in the cosmos is fueled by the very same qualities we cherish in ourselves: curiosity, collaboration, and a stubborn hope that with enough care and courage, the universe will eventually share its secrets. This decade will be a crucible for our cosmic story, and the fire is already lit. We stand at a fork in the road, with each possible path leading to a radically different future for our understanding of everything. Let us map out the 4 most likely destinations that could emerge from the data gathered in the next 10 years. The first and perhaps most humbling outcome is that we find a subtle, persistent error. The James Webb Space Telescope, alongside the Vera Rubin Observatory, could finally identify a hidden systematic flaw that has evaded us all this time. Perhaps a universal property of interstellar dust or a subtle evolutionary quirk in Cepheid stars has been biasing our local measurements. This discovery would be a monumental triumph of scientific rigor, not a defeat. It would reconcile the numbers, affirm the elegant lambda cold dark matter model, and solidify our current cosmic framework. Cosmology would enter an era of precision refinement, using our now perfected tools to explore the finer details of dark matter and dark energy within a stable, trusted paradigm. The universe would be a known, if still wondrous, book whose basic plot we had finally confirmed. The second path leads not to an error but to an addition. Imagine that early dark energy, or another form of new physics, is confirmed by multiple, independent lines of evidence. Data from the cosmic microwave background, combined with the large-scale structure maps from new observatories, might show the unmistakable fingerprint of a dynamic force that briefly surged in the universe's infancy. This would not shatter our model but evolve it. We would graduate from lambda cold dark matter to lambda cold dark matter plus, a revised recipe that includes this transient ingredient. It would be a historic expansion of the cosmic rulebook, showing that the vacuum of space itself has a richer, more eventful history than we ever suspected. Cosmologists would then race to understand the nature of this early force and its connection to the dark energy dominating our present era. A third, more disruptive possibility is that the tension does not resolve, but instead multiplies. Gravitational-wave astronomy, with its pristine, independent measurements, might mature and deliver a third, definitive value for the Hubble constant. What if this new number agrees with neither the local nor the early universe measurements? What if it points to a value entirely its own? Such an outcome would be the most electrifying and the most challenging. It would suggest that our fundamental assumptions about cosmic geometry or the nature of gravity itself are flawed. This would not be a simple addition to the model, but a demand for a complete paradigm shift. The comfortable framework of lambda cold dark matter would be set aside, and theorists would be tasked with building a new cosmology from the ground up, guided by this trio of conflicting clues. It would be a period of glorious, chaotic revolution in our understanding of reality. Finally, we must consider the possibility of enduring mystery. The discrepancy might simply persist, hardening into a permanent feature of our cosmic maps. As our measurements become ever more precise, the gap could remain statistically solid and utterly inexplicable. This would be a profound and poignant outcome. It would mean that for our generation, and perhaps the next, the universe holds a secret just beyond our grasp. This unresolved tension would become a permanent question mark in every textbook, a quiet reminder of the limits of our current knowledge. Yet, even this path deepens our understanding. It teaches a powerful lesson in intellectual humility, proving that the cosmos is under no obligation to conform to our models or timelines for discovery. It would ensure that the greatest questions remain alive, a beacon for future minds armed with tools and ideas we cannot yet conceive. Each of these futures, from quiet confirmation to total upheaval, promises progress. Whether we are correcting a subtle flaw, adding a new chapter to physics, rebuilding our entire framework, or learning to live with a beautiful mystery, the journey itself refines our vision. The next decade will not just give us an answer, it will show us what kind of universe we have been living in all along. The measurement discrepancy in cosmic expansion is far more than a technical glitch in our instruments. It stands as a brilliant beacon, its persistent light pointing directly toward the vast and thrilling unknown. We have journeyed together across this cosmic landscape, from the brilliant flash of local supernova to the faint, ancient whisper of the primordial cosmic microwave background. We have followed the meticulous detectives hunting for hidden errors in their data, and we have listened to the bold theorists sketching visions of revolutionary new physics. Along the way, we have seen how this single, stubborn number connects to the very technology we build, the philosophical questions we ask, and the boundless human curiosity that drives us to look up. Whether this journey ultimately leads to a subtle tweak in our most successful model or a wholesale rewrite of cosmology's foundational rules, one profound truth has emerged with crystalline clarity. Our universe is more mysterious, more dynamic, and more wonderfully strange than we ever dared to imagine just a generation ago. The great astronomer and storyteller Carl Sagan once reflected that somewhere, something incredible is waiting to be known. The Hubble tension is not a barrier to that knowledge. It is our direct invitation to go and find it. This cosmic detective story is still being written, with new evidence arriving every time a telescope opens its eye to the sky. If you found this journey to the frontier of understanding compelling, consider subscribing for more explorations of the great mysteries that shape our reality. And we would love to hear your perspective. What do you believe lies behind this cosmic discrepancy? Share your thoughts in the comments below.